Okay, everyone, welcome back to CSE 373. Today we're going to continue our discussion of disjoint sets. In this particular video, I'm mostly going to be doing review of what we saw on Monday. The reason is the stuff we're going to talk about today is kind of important for understanding the runtime of these operations and also can serve as helpful tips for when you go to implement Project 4. And kind of to synthesize all the things that we're talking about today in what we talked about on Monday, it's important to kind of recall that information to help us contextualize what we're seeing today and relate it to what we saw previously. So this video, I'm going to kind of do as quick as possible of a run through of what we saw on Monday and kind of stress some things that we didn't spend as much time on. And then in the remaining videos, we're going to be talking about more specifics on a couple extra optimizations to make to the structure and why that helps. As a reminder, I don't have an announcement slide for this today, but I got a little mixed up with my days earlier. So today, this video is for Wednesday. This is the day that Project 3 is due. So make sure you turn that in tonight, and do remember you do have access to late days. So in terms of our learning objectives for today, we want you to be able to implement the weighted quick union and describe why making the change protects against this worst case runtime, implement this idea of path compression, describe how this, what contributes to the runtime of prims and cruscles, and kind of to be able to implement this disjoint set structure using arrays as the backing. Those are kind of our big learning objectives for today. As a bit of review, we have been talking about this idea of minimum spanning trees. We wanted to find a minimum kind of covering of the graph, one that uses edge weights that have minimum sum of total edge weights. We want this thing to span the graph to connect or to touch all the vertices, and we want it to be a tree. There's exactly one path between any two. So this set of edges forms this minimum spanning tree. And we kind of highlighted that minimizing the sum of these edge weights is not the same as minimizing shortest paths. MSTs will not necessarily find you shortest paths. They just find you a set of edges that cover the graph with minimum total cost. If a graph is connected, it will have at least one minimum spanning tree. So these are some things we maybe kind of took for granted, but something that will be true. So if the graph is connected, that means there will be a minimum spanning tree. We almost always talk about minimum spanning trees on undirected graphs. We won't talk about them with directions. It makes it a little bit more complex and not as intuitive as kind of the definitions for the undirected case. Now, if the graph is connected and has all unique edges, meaning there's no duplicate edge weights, then there's going to be exactly one minimum spanning tree. It's going to be kind of all of the minimum edge weights that don't form a cycle. So if you have unique edge weights, you're going to only have one MST. However, if you have duplicate edge weights, meaning that multiple edges share the same weight, there may be multiple valid minimum spanning trees. And sometimes you'll end up with different ones from cruscles or prims, in some sense because the way they break ties is different. And so whenever you break this tie case, you might end up with a different but still valid minimum spanning tree. So on this right, I show one graph that has two minimum spanning trees. And it really comes to the fact that two of those edges there have weight 3. We also talked about the idea of in Kruskal's algorithm, where we're kind of going edge by edge, grabbing the smallest edge possible. We really needed the structure to be able to figure out if two graphs have already been added to the same kind of island. So Kruskal's kind of builds out these islands, always grabbing the smallest edge that connects two unconnected islands, and then merges them together. We really needed the structure to say, like, are these two vertices in the same set for Kruskal's? And to be able to then union them, which motivated this idea of the disjoint sets ADT, also called union find, which is the structure that lets you operate on this family of sets, figure out if they're in the same set, if an element is in the same set as another, and to allow you to union two of these sets together. And so Kruskal's kind of goes through edge by edge using this disjoint set structure. And in the last day of lecture, we kind of did kind of a progressive implementation of this disjoint set ADT. And today we're going to kind of pick up where that left off. But I quickly want to recap kind of how we went about implementing that. So we started with quick find and quick union. And it is a little confusing that we name them so similarly, but we're trying to highlight kind of what their purpose is, what they're trying to optimize. Quick find, if you look at this table down here, is optimized for the find operation, trying to find which set does a particular element belong to. While quick union is kind of optimized for union being fast, unioning two sets together. Now, we talked about quick find as being a map from kind of the value in a set to which set it belonged to. So for example, Eileen is in set 1, Joyce set 2, Santino set 1. Now, we kind of thought about these disjoint sets as being, like an abstract sense, kind of these separated islands. But the implementation, we just said, okay, for each value, here's what set it belongs. Now, a totally valid other implementation was quick union, where we use this idea of up trees to keep track of parents. Both of these structures implement the idea of a disjoint set. They're just different implementations and have different trade-offs. Quick find is optimized for finding. Quick union is optimized for unioning. One thing I want to mention, because sometimes you'll see this out there, is this quick union or quick find. We always talk about them as using an ID to identify each set. So all of the values in this set we said belong to set 2, and we stored that ID at the root. Another totally valid thing to do, which a lot of implementations use, is to pick one representative from the set. So instead of having an ID 2 for this set, you would say that Joyce is the representative. So whenever you call find on Alex, it would return Joyce. They're just different implementation details, but it's the same exact idea. Now, when we talked about how to union this quick union structure, we talked about some pseudocode to go about kind of doing this. And I wanted to kind of highlight, I'm going to hide my video for a second, one place where it overlaps. I wanted to highlight kind of some confusion about how to implement this union. So when we're talking about quick union and we wanted to union two sets, we want to union Ken and Santino. And suppose that our structure currently had the state up here. We talked about kind of 3 implementations. This first one that worked found the root of your first argument. So let me pull up my pen. It found the root of the first argument. So find A. So in this case, Ken. We find Ken's root, which is Joyce. We find then Santino's root, which is Eileen. And then we set root of A to point to root of B. So we had Joyce point to Eileen, which is exactly what we got here. Now, we talked about one implementation that didn't work here, where you thought, well, maybe what if I just find the root of B and then set A to point to the root of B? Well, here, A, in this case, the first thing was just Ken. So if we make Ken point to the root of the second tree, well, then we've kind of separated Ken from Joyce, where he was supposed to be before. We didn't associate all of the elements in that first tree to the second one. Disjoint sets don't have this notion of separating things that were in a family before. So if you're going to join Ken with Santino, you have to join all of the values in Ken's set to all of the values in Santino. So that almost always means changing the roots. Now, we talked about a third implementation that technically works. So one thing you could do is find the root of A and then have the root of A point to B. Now, this technically works because you're modifying the root. You're saying, okay, find the root of A. In this case, it was Joyce. Go ahead and move that to point to B. So make Joyce now point to Santino. Now, this technically works because it joins all of Joyce's family to Santino, and that associates them to all of Eileen's set. But this is going to be an inefficient solution. And the reason is it's going to unnecessarily increase the height of the tree, because now we're putting Joyce underneath Santino. We now kind of incur the height of tree B on top of tree A. So even though it's a little bit more complex to go up the tree both times, I'm going to go ahead and show my camera so I could show my animation or show my me walking through, like climbing up the trees. Even though that takes more time, it's going to save us time in the future because it makes the tree shorter. So I wanted to highlight this importantly, 3 types of ways of implementing union. You're going to want to implement this first. The second one just doesn't work, it's broken. And the third one's inefficient. So that's why quick union can kind of get us this. But quick union still has a worst case runtime. That's an important thing to highlight. So that's where we kind of talked about this idea of weighted quick union, was add an implementation detail to quick union to always put the smaller tree underneath the larger tree. The idea being that if you had this kind of worst case runtime with quick union, you could union A to B, and if we always put the left tree under the right, and then B to C, maybe I'll make it point this way, and then C, you can make this kind of worst case linked structure. The idea was the one modification in weighted quick union was change this line of code. Instead of always putting root A under root B, figure out which one's the smaller tree, and then put that underneath the larger tree. So then we would get something like, like this tree. We always put the smaller one under. And this makes sure that the height of our tree is not too small. Now, you might be wondering, wait, how can we guarantee that if we're just counting the number of nodes? And we walked through this little example of actually counting up kind of for these nodes, what's the height of this tree? So if you had one node, the worst case height is 0. If you had 2 nodes, the worst case height is 1. Then we skip 3 because that's just not interesting. We're just going to go in powers of 2. That's kind of like the maximum number of nodes you can get. So then we go to 4 nodes. And the worst thing to do is if we unioned 2 nodes and 2 nodes together to get 4 nodes, then this weighted quick union would just choose one of them arbitrarily to be the top, and we put the other one underneath that. Now, importantly, what we're doing here is we're kind of building up this worst case by construction. So we're saying like, okay, this is the worst case tree with 4 nodes in it. So now if I want to make the worst case tree with 8 nodes in it, I might consider trying to union this worst case 4 with another worst case 4. Now, what did this weighted quick union say? Well, it says, oh, they both find the roots of both. They both have the same number of nodes, so just make one of them the top. And so then you get this kind of goes underneath. And we kind of went through all of this and we argued that, hey, if we look at the relationship between the number of nodes and the height, then we can see that we get this logarithmic growth, that we are able to double the number of nodes each time before increasing the height by 1. So then our tree height is going to be worst case log n. Now you might be wondering, why did we use heights, or why did we use weights instead of heights? So importantly, we use the number of nodes in the tree to determine its weight, not the height of it, like we would with AVL. Heighted quick run, if you talked about it in terms of height, this would work, but it would give you the same asymptotic runtime. So I would argue that it's much, much easier to keep track of the weights, just the number of nodes, and it gives you the basically same runtime. So this is one case where we try to keep it simple because it works. So both of them could work, but I would argue that weighted quick union is just going to be simpler to implement. So I suggest. So, and then kind of to wrap up everything we've seen so far is we've talked about 3 different implementations of this disjoint set ADT. And we talked about kind of how their runtimes are affected by the choices they make. We importantly highlighted that one use case that's important is making sure that union is fast if you know you're unioning together 2 root nodes. Why is that? Because Kruskal's always just find before union. So it's really, really helpful to ensure that, and to consider the case of, well, what if I'm calling union on 2 things I know are roots? Then this weighted quick union and quick union have that theta of 1 runtime. Now, what we're going to talk about in our next video is one kind of last optimization and kind of how we think about this algorithm called path compression. But we'll talk about that in our next video.